This is the sixth lecture, which is the last part of this chapter, and we are still talking about introduction and basic concepts. Chapter 1, Introduction and Basic Concepts, and as you know, I covered main concepts and no slip condition the first two lectures. The third lecture I talked about brief history. The fourth was dedicated for classification of fluid flows. And the fifth was about system and control volume. And now this is my topic, which is importance of dimensions and units. Okay, so this is the main topic, importance of dimensions and units, and this will be mostly a review of what you have studied before. Okay, the first question is, why is it important to study dimensions and units? Think about it for a few seconds. Okay, to answer this question, let us look at this part from a newspaper that was issued in 1999. Loss of Mars probe blamed on math conversion error. NASA scientists apparently failed to change English units of measure to metric. So this was a mistake that was done by NASA scientists in 1999, and it costed them 125 million spacecraft. So this was done long time ago, and if this error to be repeated, the cost will be much more now. So even though it is a simple thing, and you can do it quickly and easily, but if you miss it, it might lead to catastrophe. لا تغلط فيه ممكن يؤدي إلى كارثة, even though it is a small thing. So this is why it's important to consider dimensions in units. So what is meant, or what are the dimensions? First of all, what's meant by dimensions? So any physical quantity can be characterized by dimensions, and the magnitudes assigned to the dimensions are called units. Okay, magnitudes assigned to dimensions are called units. Let me ask you this question now. What are the 7 fundamental or primary dimensions, and what are their units in the SI system? Okay, so you know that some basic dimensions such as mass, length, time, temperature are selected as primary or fundamental dimensions. Those are primary or fundamental dimensions. However, velocity, energy, volume are expressed in terms of the primary dimensions. So, for example, the velocity is length per unit time. So this is why you can express those, let us say, those dimensions by the fundamental or primary dimensions. And this is why velocity, energy, volume, they are not called the primary dimensions, they are called secondary or derived dimensions. So we have the primary dimensions, which are here, or fundamental, and we have secondary dimensions, which are here. For example, velocity, energy, and volume. Okay, regarding the 7 fundamental or primary dimensions, we have them here in this I system. So, for example, length is a primary dimension, and the unit of its meter. Mass is another primary dimension, and the unit of it is kilogram. You have time, and the unit of it is second. You have the dimension of temperature, and the unit of it is Kelvin, and electric current, which is an ampere, amount of light, candela, and finally amount of matter in moles. So those are the fundamental or primary units, and those are the fundamental or primary dimensions in the SI system. So you know that we have two sets of units which are still in common use today. We have the English system of units, which is also known as the United States Customary System, USCS. So they mean the both, I mean, it's the same thing, they mean the same thing. And then we have the metric system, the metric SI, which is also known the international system. So here I'm raising a question for you. Why we say international system, however we say SI, why not IS? So I will keep this question for you. Now, some SI and English units, so the mass and length units in the two systems are related to each other. So you know that 1 pound mass is equal to 0.45 of a kilogram. So almost 1 pound mass is equal half a kilogram. And 1 foot is almost equal to 1/3 of a meter or 30 centimeters. So 1 foot is one ruler long. Not the small one, this is like a medium one if you want to say, which is 12 inches. So this is not the ruler that you put in your pen case or pencil case. Now I want you to think, what do we mean by force, weight, specific weight, and work? How can you define these four terms? So take a few seconds and think about them. And what is meant by Newton and what is meant by bound force. Also, just take a few seconds and try to define what is Newton and what's bound force. Okay, so let us start with the force. So force is considered as a secondary dimension. You know this, it is not a primary or fundamental, whose unit is derived from an equation based on Newton's blah 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 law. So which law? That is which Newton's law that defines force, which is this force is equal to mass times acceleration. F is equal to ma. So which law is that? The first, the second, or the third? So you know this is Newton's second law of motion because Newton's first law is about inertia. The second law is about the relation between the force, the mass, and the acceleration. And the third one is about the action and reaction. For every action, there is an equal and opposite reaction. So then if I want to, for example, define a Newton, so I will say a Newton is the force required to accelerate 1 kilogram at an acceleration of 1 meter per second square. However, a bound force is the force required to accelerate a mass of 32.17 pound mass at an acceleration of 1 foot per second square. So this is the definition of bound force, and this is the definition of Newton. So 1 Newton is equal to this, 1 kilogram times meter per second square, and bound force is equal to 32.174 pound mass times foot per second square. So this is the definition of the Newton and the bound force. Okay, this is about the force. What about the weight? So the weight is the gravitational force applied to a body, and its magnitude is determined from an equation based on Newton's second law. So the force here is the weight, the mass is the same, and instead of the acceleration we have g, which is acceleration due to gravity. And you know that the unit of the weight is Newton. So the weight, so this is for the weight. And then for the specific weight, the weight per unit volume of a substance is called the specific weight gamma. So specific weight is the weight per unit volume. It is weight per V, per unit volume. And is determined from gamma is equal to rho g. Gamma is equal to rho g, where rho is the density. So this is the definition of the specific weight and the definition of the weight. Work can simply be defined as the force times the distance. So therefore it has the unit of Newton times meter, which we call joule. So 1 joule is equal to Newton times meter. 1 joule is equal 1 Newton times meter, and also you are familiar with this from previous courses. Now let me ask you this question. What do we mean by BTU and calorie? What does BTU stand for? Okay, let me answer those questions. So in the English system, the energy unit is the BTU, which is also called British, or BTU, which stands for British Thermal Unit, and it is defined as the energy required to raise the temperature of 1 pound mass of water by 1 degree Fahrenheit. So if you take 1 pound mass of water, which is almost half a kilogram, and you want to raise its temperature by 1 Fahrenheit, then you have to give it 1 BTU of energy. On the other hand, in the metric system, the amount of energy needed to raise the temperature of 1 gram of water by 1 degree centigrade is called 1 calorie. 1 calorie is the energy required to raise the temperature of 1 gram of water by 1 degree centigrade, and 1 calorie is equal to around 4.2 joules. So I am in a position to ask you a question here. Which is larger, a calorie or a BTU? Take a moment, think about this question. So actually, 1 BTU is almost equal to 250 calories. 1 BTU is almost equal to 250 calories. Why? Because for 1 BTU, you need much more quantity of water to be raised by 1 degree than it is for a calorie. For a calorie, it's just 1 gram. However, for a BTU, you need 1 pound mass, which is around 500 grams. Okay? Now, another important concept here it is called the dimensional homogeneity. So in engineering, all equations must be dimensionally homogeneous. I mean, the same equation, you cannot add, for example, length with mass. So all the equation must be dimensionally homogeneous. That is, every term in an equation must have the same dimension. So all the terms, the same equations must have the same equations. Actually, every term in an equation must have also the same units. So you cannot add foot to meter. You have to convert one to the other so that your calculations will be correct. So dimensional homogeneity means each term and equation must have the same dimension, and actually you have to have even the same unit for your calculation to be correct. Those are called the unity conversion ratios, that's the one you see here. So all non-primary units, secondary units, can be formed by combination of primary units. You know this. So for example, force units can be expressed as, so Newton is equal to kilogram times mass per second square. Bound force is 32.174 pound mass foot per second square, which is something that we talked about before. So the unity conversion ratios, they can also be expressed more conveniently as unity conversion ratios. So if you take Newton divided by kilogram times meter per second squared, this will give you 1. This is why it is called unity conversion ratios, because it's equal to 1. And also if you take 1 pound force divided by 32.174 pound mass times foot per second squared, this will give you 1. The same applies to watt per joule times second, or 1 kilojoule divided by 1000 Newton times meter. The same thing applied to 1 kilopascal divided by 1000 Newton per meter square. So this is about the unity conversion ratios, and this ends this chapter, and whatever is remaining will be just to solve problems for you related to those um, unity converging ratios, and the other concepts discussed in this chapter.